Hi, hello, welcome to Came Cloud. So we'll continue with structure determination from spectral data. This is our session 3. I hope you have gone through session 1 and session 2 as well. So we'll continue with next problem. This is problem number 5. Deduce the structure of a compound based on given spectral data. Molecular formula is given as C6H6O. So here we have one oxygen atom, then IR. In IR, we have four peaks which are given here: 2720, 2100, 1685, 1610. So here 1610 is for C double bond C stretching of alkene. 1685 can be for C double bond O stretching. 2100, this can be for triple bond C triple bond C, and 2720, this can be for CH stretching of aldehyde. Right, so we'll see details of this. This is a preliminary observation we are writing. Then in H1 NMR we have four peaks. Right, so there are four different groups of equivalent protons. Here they have given C13 NMR also, so we have 6 peaks for 6 different carbon atoms. Right, so we'll see these as well. So firstly we will calculate site of unsaturation from molecular formula. So here we will compare with formula for saturated hydrocarbon CnH2n plus 2. So for C6 it should contain 14 hydrogen, C6H12. Here we have C6H6. So there is deficiency of 8 hydrogens, right? So site of unsaturation must be 8 divided by 2, it should be 4. So site of unsaturations for this compound must be 4. As we have seen in the preliminary observation, it may contain C double bond C, C double bond O, and C triple bond C. So one site of unsaturation for this alkene, one site of unsaturation for this carbonyl group, and one site of two sites of unsaturations for this C triple bond C. So there are total 4 sites of unsaturation. So this is matching with our preliminary observation. Then in IR we have 2720. So in 2720 is for CH stretching of aldehyde. CH stretching of aldehyde. Right. This usually appears near 2750 centimeter inverse. It gives two peaks, 2750 centimeter inverse and 2850 centimeter inverse. Right. So this may merge with the CH stretching of CsP2H, hydrogen attached to sp2 hybridized carbon. We will see these details in fundamental vibrations of IR. But in case of aldehyde, we'll get one peak near 2750 centimeter inverse. So here they have given 2720, which is for CH stretching of aldehyde. Then we have 2100. See, this 2100 is for C triple bond C stretching of alkyne. Right, so this region near 2200 centimeter inverse is for triple bond. It's for both, like C triple bond C or C triple bond N. There is no nitrogen, so we are not going with this possibility. It must be alkyne. Then 1685 is for C double bond O stretching of carbonyl. Right. So this is the lower value, quite lower value. We have discussed earlier that for ketone, C double bond O of ketone may appear at 1715 centimeter inverse. Right. And this is quite lower value. So lower value for C double bond O stretching appears for amides. So this amide CO appears around 1670 centimeter inverse. There is no amide, so this must be ketone, and this value is lower. So this must be not ketone. This must be ketone or aldehyde. It can be aldehyde, which we have discussed aldehyde here. So it must be aldehyde, right? Not ketone. And its aldehyde value is 1725 centimeter inverse, right? So this value is lower in this case, so this must be conjugated aldehyde. It must be conjugated aldehyde, right? Then we have 1610 also. This is for C double bond C stretching of alkene. C double bond C stretching of alkene. Then in H1 NMR we have 2.0 singlet for 9 mm. So here instead of number of protons they have given this 9 mm, 3 mm, 3 mm, 3 mm. So this is called integration. Right, so when we see this H1 NMR spectrum, near this peak you will observe this S-shaped curve. So this 9 mm which is given, this is the height or length of this S-shaped curve, right? So here we'll take these as a ratio, so 9 S23 S23 S23. So we'll take LCM of all these numbers and divide that LCM, divide these numbers by that LCM. So the LCM will be 3 in this case. So we'll get 3s2 1s2 1s2 1, right? So it can be 3h 1h 1h and 1h. So total number of protons are 6, so it is matching with this. So we'll continue with the same ratio, 3h 1h 1h and 1h. This 3 mm correspond to 1 hydrogen, right? So now we have a number of protons also. So we'll write this, this may be CH3 group. The value is 2.0 and it is singlet, so this may be attached to some quaternary carbon. Then 3.0 is again 1H, so this is CH, is maybe attached to some electronegative group, right? We're not sure. It is not attached to oxygen, because if it is attached to oxygen the value may be more than 3.6, right? This is 6.2, a doublet, J is equal to 3 Hertz. This is for 1H, so 6.2 ppm. This is region for alkene, so the peak between 4.5 to 6.5 ppm. This can be for peak of or protons of alkene, right? So here we have 6.2 ppm, so this must be alkene H, right? So it is giving doublet, so there is one more proton in the vicinity. If you observe this C and D, here we have J is equal to 3 Hertz, here also we have J is equal to 3 Hertz. So these two protons may be coupling with each other, right? This D is 9.9 ppm. So 9.9 ppm, this is for aldehyde. So 9 to 10 ppm, this is the region for aldehydic proton. So this proton must be proton of aldehyde. This is appeared as a doublet. This has appeared as a doublet. So there must be one more proton in the vicinity of this. So this is a conjugated aldehyde, right? So this H is coupling with this H. So we are getting doublet for this with J is equal to 3 Hertz, and doublet for this aldehyde H with J is equal to 3 Hertz. So this type of system must be present in this compound. Now we'll try to derive structure based on whatever the fragments we have. So what we have is, just a minute. Yeah. So what we have here is, we have this conjugated aldehyde, C double bond O H is 1H on this, right? So this has appeared as a doublet with J is equal to 3 Hertz. This has appeared as a doublet with J is equal to 3 Hertz, and this IR data is also supporting for conjugated aldehyde. So we'll go with this, right? Then we have C triple bond C present in this compound, right? And there is one more H we have left with. So we have used 1, 2, 3 and one more CH3 also, 6 carbon. So we have CH3, C triple bond C, and this conjugated aldehyde. So we have 1, 2, 3, 4, 5, 6 carbons we have used here, right? So for this alkyne we have this 2 valencies which are pending. This is 1 valency which is pending. This is, here we have 2 valencies which are pending. So we need to connect something here. So this H we need to connect to this alkyne. So this will match, because alkyne proton can appear around 3.0 ppm and this is singlet, right? So it will it must be proton of alkyne, right? So now we have this alkyne fragment and this methyl fragment, so we can connect this to this conjugated aldehyde. So I'm writing CH3 here, and I'm writing this C triple bond C H on this. So this must be the structure of the compound. This must be the structure of the compound, right? We have C13 data also. We'll try to match with the C13 data. So we'll rewrite the structure here. This is conjugated aldehyde, so one H present on this. Then we have a C triple bond CH, and we have a CH3 on this. So here in case of C13, if you observe, they have mentioned this quartet, singlet, doublet, doublet, this splitting. So in this case, in C13, this multiplicity is giving idea about how many protons attached to that same carbon. So this has appear as a quartet, then this must contain 3 hydrogen. So this is pick for methyl group. So for this methyl group, right, which has appeared around 24.0. So this is for this methyl group. Then we have this 81.0 singlet and 88.0 doublet, these two peaks, right? So these are for alkynes. Alkyne, this is in the region of alkynes. So these are for alkynes. So this doublet wala 88 is for this carbon, and this 81 is for this carbon, right? Then we have alkene. So these two peaks are for alkene carbons. So this 135 doublet must be for this carbon bearing hydrogen. This is for 135.0, and this is a quaternary, so this must be 142. This has appeared as a singlet. This has appeared as a singlet, so this must be this one. And this is a carbonyl carbon, so 192, right? So this carbonyl carbon in C13 appears at a higher value, so it should be above 200 most of the time, above 200. But if it is conjugated, then it may appear below 200 ppm, right? So it has appeared as a 192 ppm. So this also supports the presence of conjugated carbonyl. So this must be the structure for this compound, right? Thank you so much.